Okay, so that's a possible explanation for these hot Jupiters, but what about these eccentric giants like 70 Virginus, these things that are further out with very elliptical orbits? What can we do about them?
Well, is it just on its own? Is that just an isolated case so we don't have to worry about it, or is it pretty common?
Well, here are the data. Again, we've got a time lapse showing how these things build up. Now we're plotting, once again, how far out they are, but now we're plotting the eccentricity. Eccentricity of 0 means a perfectly circular orbit. Eccentricity of 1 would mean a parabola. So the more up here, the bigger the ellipticity is, the closer and further it goes. And what you can see is the ones that are close in actually aren't very eccentric. Eccentricities of 0.2 or 0.3 or a bit less.
But that kind of makes sense, because if you're a big planet and you're near the sun, you're going to get bent all out of shape by the tides, where the sun's pulling on one side of you than the other, so that's going to cause friction, which is going to mean you're going to try to limit that. Best way to do that is to go in a circle.
Yes, so it turns out if you do the calculation, you bring a planet close, it will raise big tides in the star, and these tides will actually tend to what's called circularize the orbits. So you'd expect anything this close in to be in a pretty much circular orbit, and
Right.
indeed they are. But you look at the ones further out, and oh my goodness.
Yeah, so this is 1 AU, so that's the distance of the Earth, and here we have Jupiter, and we can see all these things. I mean, these things are coming in on comet-like orbits. Not at all. They don't look like planets. They certainly don't look like the Earth or Jupiter.
Yes, everything in our own solar system, Jupiter has an eccentricity of about 0.05, which would mean it's almost everything we're seeing is far more eccentric than almost anything in our own solar system. So that's a bit weird. How are we going to produce this? I mean,
Well-
the problem is, you're forming things out of a protoplanetary disk. The disk is going to be in circular orbits. It has to be, because gas can't be in elliptical orbits, because it would bump into other gas and equalize out. So you're forming things from a circular spinning disk. They should, damn it, be in circular orbits.
Well, so what happens if you just go out and try to simulate it and make sure that your intuition is right?
So now we're going to do the reverse. What we were talking about last time was we were using the disk to cause things to spiral in. It does that very slowly, keeping them in nearly circular orbit as it spirals in. But let's say we form the planets and then get rid of the disk. In this case, there's nothing left to stabilize them, but if you've got enough planets close together, they'll start influencing each other. So here's a simulation. I'll give you the code so you can play with it yourself. So I put a bunch of things in random orbits, and you can see they're all interacting with each other.
Like this one had a close collision.
Yep.
And presumably when things interact, if they get too close, one of the ones gets thrown out, usually the smaller of the planets.
So you can see this green one here is now in a pretty eccentric orbit. Oop, it crashed in. Oh well, it wasn't anymore. But this a whitish one over there is now in an eccentric orbit. So in this case, everything will start off in a circular orbit, and you did actually end up with some elliptical orbits simply because of the interactions. But it doesn't always work. Here's another run of the same code. So once again, they start in circular orbits.
So here you've done exactly the same thing. You've just started things out with a different random set of conditions.
That's right. And so you have the code you can play for yourself and see what you get. And what are we getting over here? Lots of collisions again. There's another collision in the middle. And this time you end up with this one. Crashed in with that one.
Ooh. It's one way to make a big a new planet.
So now we've got something that's actually fairly big, fairly close in, but it's in a fairly reasonable circular orbit, not too eccentric. So maybe this would do it, a game of sort of billiards, a crapshoot if you like, where just random interactions. So you need to have lots of things, get rid of the disk, and then have them interact by their own gravity.
Okay, but so you end up with one object here. It seems to me that you're going to, whatever you get, you're going to end up with one object, because everything else is kind of Gonski.
Yeah.
Gets thrown out of the system. It doesn't look at all like our own solar system.
Yes, here's our own solar system, and you can see the things are pretty damn near circular. So, once again, the problem is might be too good an explanation. If you do get these huge numbers of planets all playing billiards, first we get lots of collisions, and secondly, you don't get anything like our own solar system.
Right. I mean, the advantage of going in these nice circular orbits is they don't cross each other, and you don't play billiards. As soon as you start throwing planets in on these elliptical orbits, there are going to be collisions, and you're going to rearrange the system in pretty short order. Guaranteed.